This is the presentation for cycle theory of pre-process pulses for large memory arrays. Here's the simplified the non-flash memory device, and memory cells connected to a single word line. And in this case, the 1K cells are connected. And each cell can be connected to its own bit line, and each bit line is connected to sensor amplifier. Here's the threshold voltage distribution. For example, half of 1K cells have the data 0, and the other half member cells have data 1. When you apply the voltage on the gate of each member cell here, then the cell with data 0 flows the cell current because the threshold voltage lower than the gate voltage. Then the bit line should be discharged. On the other hand, the memory cells with data 1 doesn't turn on with this gate voltage. Bit line voltage should be kept the same as the pre-charge level. Sensor amplifier senses the bit line voltage lower or higher than the reference voltage. Then the sensor amplifier can detect the data of each memory cell and latch the data 0 or 1. This sensing and amplifying operations are done simultaneously in the 1K sensor amplifier. After that, the data is transferred from first sensor amplifier and then from the second and so on to the NAND controller device. Because word line has significantly large parasitic resistance and capacitances, therefore even the nearest word line goes high in a very short time, the further cells require some amount of delay time due to large RC delay. Bitline sensing operation cannot start before all the gate voltage reach to the target voltage, because sensing operation is done simultaneously, and therefore the lead access time is composed of word line delay time, bit line delay time, and I/O delay time. Among them, the word line delay time is the major term. Therefore, NAND flash memory designers must minimize the word line delay time for first access to NAND flash. How you can accelerate wordline delay? Here's the wordline delay model. If you concentrate on the selected wordline, it be modeled like this. When the step pulse is applied, the farthest wordline behaves like this. To reduce the delay time, it is well known that pre-emphasis pulse can reduce the delay time. This technique was already presented early 90s, but recently the NAND flash, 3D NAND flash, needs to use this technique because the RC delay time of wordline has been prolonged significantly than the 2D NAND flash. What was the problem to design the pre-emphasis pulse? Because of a lack of the circuit theory for the pre-emphasis pulses, designers must run various simulations by changing the pre-emphasis pulse width to identify the optimal pulse width to minimize the delay time. And therefore, the aim of this work is identifying exact solution of borderline behavior. Then we want to find the design equation with pencil and paper. To find the optimum pulse width as a function of pulse height and delay time as a function of the wordline RC time constant, wordline pre-emphasis pulse height, and then the definition of delay time. So there are various wordline circuit equivalent models. The simplest one is this RCG model, and G indicates grounded. Another model is RCCC. C indicates coupling to the next neighbor word lines. The general one is like this. Both CG and CC are included here. So this model includes both 1 and 2 cases, and at the extreme cases where CC is 0 or CG is 0. Another concern is driver or switching resistance between the generator and word line. If you add the resistor term here, then this resistance should affect the word line behavior, of course. These discussions were included in this presentation. However, we noticed that this most simple model can include the fundamental behavior You can get the equations for the other cases, but the result showed that only the difference is only in a proportional coefficient. So main term can be extracted from this model. Therefore, in this presentation, I will focus on this model. Here's the parameters definition. Capital E indicate the target voltage of the word line. Alpha shows the preemphasis. So alpha must be greater than 1. T pre shows the preemphasis pulse width. X shows the position of word line. 0 indicate the nearest, and L or 1 indicate the farthest. We will find the exact solution, the voltage at any position x and any time t. Assuming this waveform is from the slowest node of word line, then you can define the delay time t delay by specifying the parameter beta, which indicates that the slowest node leads to the beta e. For example, if you want the 1% variation or fluctuations among all the memory cell gates, then you know the t delay as a function of beta. So in this model, you just pick up one element like this, and current and voltage I and E. You will have two partial differential equations here, and here's initial and boundary conditions. At time 0, all the position x are grounded. Second condition shows at the furthest node must be 0 current at any time t, because the farthest node is open. This equation shows that the nearest position has this strict voltage behavior given by this. The first equation has been solved in the middle of the 19th century. So what is new in this work is finding the voltage exact solutions after preemphasis pulse. So during this period, the initial condition must be here, which varies by position. But that voltage distribution can be identified by the first equation. You can input t pure to t. This shows the initial conditions for the second period. You can find the solutions to meet these two equations and the initial conditions. Then finally we reach this equation. To validate this equation is correct, we fabricated a circuit like this. We put analog buffers at several nodes to measure the internal node. Here's the one node, the results, time versus voltage. In this example, we apply 1.6 volt at the beginning. After a certain time, which is the optimum time, pre-emphasis time for this case, and then we go down to the 1 volt. This curve shows the measured, and dotted line shows the formula based on this equation. You see well matched the result, meaning this equation was confirmed to be sufficiently correct. You may wonder why we select 1/3 in addition to the farthest node. Because 1/3 is another slowest node when you apply the optimum pre-emphasis powers. This is animation. X-axis shows the position of word line. And starting point is right after pre-emphasis pass. K is the wave numbers. K equals 0 shows DC term. K equals 1 indicate the wave. So peak point has 2. Waveform of K of 2 has 3 peaks. And the waveform of K equals 3 has peak of 4. 4 peaks, peak points. As you see, as the K increases, wavelengths becomes shorter, and therefore the conversion time significantly reduces as the K number increases. Therefore, a waveform of K equals 1 determine the delay time. And as you see, this half wavelength is 2/3. Therefore, 1/3 and 1 has the slowest node. This is the reason why we selected a position of 1/3 to validate the exact solution is correct. Even we get the exact solution for pre-emphasis pulse, it is not so useful for designers to estimate the array performance or design the pre-emphasis pulse. As I mentioned here, the actual behavior is determined by k of 0 and k of 1. So you can simplify this equation to this equation. This equation has a DC term of E, which is target voltage. Therefore, you want to minimize the rest terms, especially zeroth order term determine the variation from E. Therefore, you must minimize this term, or must be 0. You can have this term equals 0 to get optimum pre-emphasis pulse. I call it as T opt, which is a function of tau. Tau is defined by here. RC time constant. And also T opt is a function of alpha, of course. But this is very simple. Therefore, you can estimate the optimum pre-emphasis pulse with us if you know the waterline RC time constant and you use what value is used for alpha. The first order term determines the actual delay time when you apply T pre of T opt. You input this information here, then the minimum delay time must be given by this equation. Minimum delay time includes RC time constant and alpha and beta. So depending on your definition for beta, you input those parameters here, then you can estimate the actual delay time for the slowest node of waterline. So these two equations are main contributions to the circuit designers who design the large memory arrays. This graph shows alpha versus delay time when you apply the pre-emphasis pulse with T opt. The blue curve shows the calculated T opt given by here. And if you apply that the pre-emphasis pulse, then you will have the delay time, minimum delay time, as shown in red curve. This mark shows the measured result, which is well matched with the theory within the 4% error at maximum. This is a beta of 0.01, 1% delay time. In this situation, if you apply the alpha of 1.6, then your delay time, waterline delay time, can reduce by 70% in comparison with the step pulse case, because alpha equal 1 indicates step pulse. You may think you don't have to have 1.6 for alpha. For example, if you apply a pre-inverse pulse with alpha of 1.3, you will have a 60% delay time reduction. Even though this value is not much than the case with alpha of 1.6, but from the viewpoint of the generator circuit, probably you won't have the lower pulse height to simplify the design. So there must be a trade-off between the pulse height and delay time reduction. So far, RC time constant is predetermined. However, in actual world, R and C should vary. Actually, plus minus 10% should be considered in the design. If the R and C varied independently, RC time constant must vary by plus minus 20%. So even if you get 70% delay time reduction, when the RC time constant doesn't vary, but actually in the worst case, you only get the 30% reduction with pre-emphasis pulse. Therefore, in the next the presentation, I will show how you can minimize this RC variation impact for reduction of worldwide RC delay time. So this graph suggests that pre-emphasis pulse design must be considered for the RC variation. That's it for this presentation, and please join me to next presentation. Thank you.